Ladies and gentlemen, it's time to start. It's 2 o'clock Moscow time, and I welcome you to the first session, Navigation Problems in Ice Conditions. My name is Ekaterina, and I will be this session convener. And our first presenter, I would like to welcome Tarovika Oleg Vladimirovich, and he will talk about ship performance in ice. Please, Oleg Vladimirovich, the digital space is yours.
Yes, okay. Good afternoon, dear colleagues. Do you see my presentation? Yes?
Yes, we see it.
And I would like to present you a study which is devoted to the analysis of the influence of the season and region of ship operation on ice performance of a ship. And first of all, I would like to say a few words regarding the relevance of this study. So all ice parameters in general could be divided into two groups. And the first group are the geometrical characteristics of ice, and they are represented by such values as total ice concentration, ice thickness, flow size, diameter, and different values. And all these parameters are geometrical in their nature. And the second group are the physical and mechanical properties of ice. And the main of them that influence ice performance of a ship most of all is the ice flexural strength. And in most of studies which are devoted to the simulation of ship operation in Arctic conditions, only the first group of parameters is usually considered, while the second group is usually assumed to be equal by some basic values. For example, ice flexural strength is usually assumed to be 500 kilopascals. At the same time, from the real practice of ice navigation, we know well that ice performance of a ship strongly depend on the season and region of ship operation. And in this study, we assumed that this influence could be due to the dependence of physical and mechanical properties of ice on the season and region of ship operation. And we tried to find some corresponding research in the literature, but actually we have found only some empirical data from 1970s and no modern research in this field. And we recognize this situation as a kind of research gap, and in this study we try to address this research gap. First of all, we need to create a link between some natural parameters and the mechanical properties of ice that influence ice performance of a ship. And we developed a special calculation algorithm. It is based on previously developed and well-known formulas, while our main contribution was that we joined them into a single computational algorithm. And the main input data is the seawater salinity, air temperature, wind speed, thickness of ice and snow, as well as some additional thermal conductivity parameters of snow and ice. And here you also see some basic assumptions of this algorithm, and I will briefly comment just a few of them. So we do not consider a case of snow-free ice, and we assume that there is also some basic snow cover, and its thickness is estimated by regression formula from Shalina and Sandven. We also assume that the change of ice temperature along thickness of ice sheet is linear, and there is a ratio of ZH that define the calculated value of ice temperature, and this ratio can vary from 0. It will be equal to the upper boundary up to 1. It will be equal to the lower boundary of ice sheet. To estimate ice salinity, we apply the formula of Rivlin, and here is the parameter A that depend on the speed of ice freezing and can change in a relatively wide range. And so this parameter forms some uncertainty. And to estimate ice density, we applied a methodology of Cox and Weeks. And to estimate ice flexural strength, we applied a formula of Timka and Dumbrani. And so based on this algorithm, we carried out some sensitivity tests. So we take in 3 natural parameters. They are seawater salinity, air temperature, and wind speed. And also we take in 3 additional parameters, internal parameters of the model. And for each parameter, we set a basic value and some range of the variation that correspond to the real observed values. And we also varied each parameter separately. And from the results, it could be seen that the most influential in the natural parameters are the seawater salinity and air temperature, because they influence ice flexural strength most of all. Wind speed was found not so seriously influencing factor. And the same situation is with internal parameters of the model. While the Z-H ratio that defines a calculation section and an average air temperature, it also has a significant influence on ice flexural strength. And we assume this parameter to be a kind of a measure of uncertainty of ice temperature in general. But in further calculations, we take the average value, so Z-H was taken to be equal 0.5. And so the most influencing weather parameters are the seawater salinity and air temperature. And our next step was to estimate how these 2 natural parameters change in space and in time. And for this, we used an open source database, and we analyzed the monthly average values of seawater salinity and air temperature. And here you see 4 pictures: seawater salinity in October and in March. And it is well seen that there is different values in different regions. For example, in Ob Bay and close to the mouth of the Lena River, the seawater salinity is on average lower than in other parts of the Arctic. And this is due to the high inflow of fresh water from Great Siberian rivers. At the same time, in the western part of the Arctic region, the salinity is on average higher than in the eastern part. And the same picture is with air temperature. And we defined 2 regions of the Arctic, eastern region and western. And they are defined by Vilkitsky Strait. And we also took 2 seasons, spring season and autumn season. And for each sector of the Arctic and for each season, we calculated an average value of air temperature and seawater salinity. And here you see that, for example, in eastern sector of the Arctic in spring season, average air temperature is minus 27 degrees, while in western it is only minus 15 degrees. Seawater salinity change is not so significant, but here you see some deviations also that depend on season and region of operation. And we use these four scenarios in our further calculations. And our next step was to build an algorithm to create an ice performance curve in level ice. And here we used quite a widespread approach. So we equate a net thrust of a ship to the ice resistance. And to estimate a net thrust of a ship depending on speed, we used some regression formula. To estimate ice resistance, we applied a Lindquist method. While here we introduced some special feature, and this is due to the fact that we will need to obtain a strict correspondence between bollard pull of a ship and ice resistance in some nominal conditions. These nominal conditions are defined by these values. So ice flexural strength is equal to 500 kilopascals, and ship speed is 2 knots, and ice thickness is equal to the maximum icebreaking capability of a ship. And here you see the equation to estimate a scale factor. And after we calculate a scale factor, we multiplied it by ice resistance values calculated for given ice conditions using Lindquist method also. And as a sample ship, we used a nuclear icebreaker built in 1972 and commissioned in 2006. The reason why we choose this ship was that it is the only ship where we have some estimations of a change of its icebreaking capability depending on season of operation. Its nominal value of icebreaking capability is 2.3 meters, while in winter, spring period, it drops down to 1.9 meter. And in summer, autumn, it rises up to 2.6 meters. And we can use this data in comparisons. And here you see the results of calculations. So we make 4 calculations for each sector, and for western sector of the Arctic, and for spring and for autumn seasons. And we see that there is a significant range of variation of icebreaking capability of a ship. For example, according to our calculations, icebreaking capability ranges from 2.05 meters up to 2.6 meters, and it will correspond to the full-scale values. And we also see a significant dependence of ship speed from the season and region of ship operation, and the thicker the ice, the more significant this dependence is. For example, in ice of 2 meter thickness, ship speed changed from approximately 2 knots up to 5 knots. And also calculated value of ice flexural strength changed from in the ice of 1.5 meters, changed from approximately 6 up to 800 kilopascals in spring, and from 3 up to 4 kilopascals in autumn season. And so, as a kind of main conclusion of our research, I can say that we found a systematic influence of season and region of ship operation on its ice performance. And we also assume that there are 2 natural parameters. They are seawater salinity and air temperature that could serve as a kind of predictors to estimate a seasonal and regional variability of ice parameters. And the other point I would like to mention is that this algorithm could be used to estimate the influence of some global weather trends in the Arctic and the influence on ice performance of a ship. So thank you for your kind attention. And if there are any questions, I will be glad to answer.